Today, we're diving into something pretty amazing. It's a pair of equations that are so simple, yet they're so powerful that they describe one of the most fundamental rhythms in all of nature, the timeless, pulsating dance between a predator and its prey. So, let's get into it and decode this incredible cycle.
So, have you ever stopped to wonder why nature isn't always, peaceful and balanced? Why, instead of finding some nice, stable equilibrium, it seems like predator and prey populations are locked in this dramatic, endless cycle of boom and bust. It's a real paradox, and it's something that puzzled scientists for decades.
And that brings us to what we can call the paradox of the pulse. Because when you first look at it, it seems like total chaos, right? A mess of ups and downs. But it's actually a very highly structured pattern. It's a kind of order that actually emerges from all that constant fluctuation.
We call this pattern a boom and bust cycle. You've got a population that just explodes with rapid growth, only to face a sudden, sharp crash over and over and over again. Now, the key idea here is this phrase, order through fluctuation. And what that really means is that this crazy, dramatic cycle isn't a sign of instability. It is the stability. The pulse is the pattern.
Okay, so how in the world do you describe this dance with math? Well, back in the 1920s, two different scientists, working completely on their own, managed to crack the code. They basically wrote the choreography for this entire natural dance. And here's where the story gets really cool. The model was discovered twice, totally independently. First, you have Alfred Lotka, who was using these ideas for chemical reactions and then for plant and herbivore systems. But then, years later, an Italian mathematician named Vito Volterra comes up with the exact same math to solve a completely different puzzle: why predator fish populations suddenly surged when fishing was halted during World War I. The same math for two different worlds? That's a huge clue that you stumbled onto something universal.
And the whole dance is choreographed by just 4 key variables. So let's meet our dancers. First up, you've got alpha. That's just the prey's natural birth rate, how fast they multiply. Then there's beta, which is how good the predator is at hunting. Next, we have gamma, the predator's natural death rate, basically how fast they die off if they can't find food. And finally, there's delta, how efficiently a predator turns a meal into baby predators.
So let's see how these dancers actually interact. For the prey, it's a pretty simple battle. On one side, you have their population growing, that's the alpha term, but on the other side, it's shrinking as they get eaten by predators, that's the beta term. The more predators there are, the more that scale is going to tip towards decline. Simple as that. And the predator's story? Well, it's basically the mirror image. Their population grows through new births, which are fueled entirely by, you guessed it, eating prey. That's the delta and beta part. But it's constantly shrinking as predators die off from starvation or old age. That's the gamma part. Their very survival is tied directly to how many prey are running around.
And this all comes together in a beautiful 4-stage cycle. First, with very few predators around, the prey population just booms. It explodes. Second, with all this food available, the predator population starts to grow, but it always lags just a little bit behind the prey. Third, the now huge predator population eats the prey way faster than they can reproduce, which causes the prey population to crash. And finally, with their food source gone, the predators starve and their numbers crash too, which of course sets the stage for the whole cycle to begin all over again.
So what you realize is the populations never actually settle down at a single stable point. That's not the goal. Instead, they're locked in this constant, predictable orbit around a central point. It's a stable dance of pursuit and escape, and it's all defined by this incredible mathematical rhythm.
But, and this is a big but, there's a catch. This beautiful, elegant model is, in many ways, completely unrealistic. And honestly, this is where it gets really interesting. Let's take a look at its world of flaws.
Yeah, this slide really lays it out. The model's ideal world is just not how things work. It assumes prey have unlimited food and that predators only eat one thing, and get this, they never get full. I mean, of course, none of that is true, right? In the real world, resources are limited, predators can eat other stuff, and the environment has hiding spots. It's messy.
So, does all that mean the model is useless? No, absolutely not. Just look at the classic data on the Canadian lynx and the snowshoe hare. The cycles are right there, plain as day. This quote sums it up perfectly. The model isn't a perfect photograph of reality, but it correctly captures the fundamental tendency for these populations to oscillate. It got the core rhythm right, even if it missed some of the finer details.
And because this simple model captured such a universal pattern, its true power goes way, way beyond ecology. It turns out this exact same cycle plays out in a very different jungle. our own economies.
So back in the 1960s, an economist named Richard Goodwin had this brilliant insight. He realized this same predator-prey structure could describe the push and pull between labor and capital. In this model, the prey isn't a rabbit, it's the employment rate, and the predator isn't a fox, it's the share of income that goes to workers in the form of wages.
And would you look at this? It's the exact same four-stage dance. When employment is high, that's a prey boom, workers have power to demand higher wages. Those rising wages, our predator growing, start to eat into company profits, so hiring slows down. That leads to higher unemployment, the prey crash, which weakens worker power, so wages start to fall, and of course those lower labor costs, the predator crash, make profits look good again, which encourages companies to start hiring. It's the Lotka-Volterra cycle, just with jobs and wages instead of hares and lynx. Incredible.
So, when you step back and look at it all, what is the ultimate legacy of this deceptively simple model?
Well, here's why it's so important. The Lotka-Volterra model was a total game changer. It was the first model to really prove that stability doesn't have to mean standing still. It can be a constant, ordered pulse. It became the absolute baseline for all modern ecological models, and it revealed a universal mathematical structure for any system in conflict, whether you're talking about biology, economics, or even things like marketing and business strategy.
So in the end, this simple structure that was first spotted in chemistry, then in fisheries, has ended up revealing a fundamental rhythm in both the natural world and our own societies. And it really makes you wonder, what other hidden dances, what other secret cycles are playing out all around us, just waiting for someone to notice?